So in the first part of this video lecture, we have proved the statement of all relevant results about operations that we can do on extended Borel functions that still produce extended Borel functions. In the second part, we spent quite a long time doing the proof that sums and products of extended Borel functions are again extended Borel functions. And now we move to the proofs that lim sups and limits of sequences of extended Borel functions are also extended Borel functions. So we move to this missing part of this video lecture. So before we move to the proofs that maximums and minimums and sups and lim sups of extended Borel functions are extended Borel functions, let's just make a small remark that from what we have seen in the previous part of this video lecture is if f is an extended Borel function, then minus f is also an extended Borel function. Now to prove this lemma, first I would like to claim it is enough to prove for the maximum only. And why is that? Assuming f and g are extended Borel functions and assumed we have proved that the maximum of any two extended Borel functions is also an extended Borel function, we can see that the minimum of two numbers, and that will be true for functions, is the same as take the negative of those numbers, take the maximum, and take the negative of that. And since we have already made this remark that comes out from the proof of the second lemma, the one related to sums and products, so we can, assuming f is an extended Borel function, we can put a minus in front of it, same for g, and now we know from the previous case the maximum is an extended Borel function, we can put the minus again and we get the minimum. So it is enough to prove it for the maximum only. And now it is enough to notice the following. For the maximum of two functions to be less than or equal to c, this will occur exactly at the points where the first function f is bounded from above by c, and the points that also belong to the set where the function g is also less than or equal to c. And these two are in f by assumption, because we assume f and g are both extended Borel functions, and sigma algebras are closed under intersection, so we can conclude that this is on f, and this is exactly what we have to prove. So from here we can conclude that this function is an extended Borel function. So this concludes the rather quick proof of this little lemma. We're now ready to move to the proof of the lemma, and you see that all the work is in proving this bit here, because then this will follow directly from it as well, and this will follow directly from these two, as well as this one, and this one also will follow from these two, or either of these two in fact. So we want to prove that this function, the function given by the supremum over natural numbers of fn, and again, what does it mean? It means for each little omega we compute the supremum, and then we call that supremum age of omega, so it's a point-wise supremum, it's point by point, it's for each omega. And we want to know whether this function is measurable, whether this is an extended Borel function. So we need to consider the event where the set where this function takes value less than a. And the proof will be very similar to the proof of this previous little lemma we just did. We just have to notice that for the supremum to be less than a, so we are considering now this set, the set of little omega for which the supremum is at most a, this is nothing but we take the intersection over all natural numbers of the sets where fn is less than a. And we can see this because if fn is less than a for every n, then omega is in this intersection, but in that case the supremum will be less than A. And conversely, if the supremum is not more than A, it means none of the Fn's can be strictly larger than A, and therefore omega will belong to all these sets here, the sets where Fn is at most A. So this completes the proof. Let's go back here. This completes the proof of this claim, that this function is an extended Borel function. To see that from the supremum, we can also conclude about the infimum. As you can guess already, similar to the previous proof, we just have to note that the infimum of Fn is minus the supremum of minus Fn, and this would then be an extended Borel function because we already know that suprema of countably many extended Borel functions is a Borel function, and we have again this remark that if a function is an extended Borel function, then minus that function also is, which proves that infimum of countably many Borel functions is also a Borel function. Now, how can we get from these two some information about the lim sup of a sequence of functions? We just have to note that the lim sup can be expressed as an infimum of countably many functions. Each function is nothing but a supremum of countably many of functions which we assume are extended Borel functions. So using the two previous cases, we can conclude as well that lim sup of functions that are extended Borel functions is also an extended Borel function. And obviously, to go from lim sup to lim inf, it's the third time we do the same trick. We already know that lim sup of a sequence of extended Borel functions is a Borel function. We already know that knowing f and r extended Borel functions, we can put minus in front of them and they're still extended Borel functions. We put a minus again here. Since the lim inf can be expressed this way, we can conclude that the lim inf of a sequence of extended Borel functions is also an extended Borel function. And finally, knowing these two, we know that if a function has a limit, or knowing only one of them actually is enough. If a function has a limit, that limit coincides with the lim sup. So if it has a limit for every omega, then since it coincides with the lim sup, and we already know the lim sup is an extended Borel function, then the limiting function also is an extended Borel function. That concludes the proof and concludes this sequence of video lectures.